Ladies and gentlemen, moving along now, I'd like to introduce Doctor Tom Forbes, a consultant paediatric nephrologist working at the Royal Children's Hospital in Melbourne. He completed his undergraduate medical training at Monash University in Melbourne, so he's at home, and then completed his paediatric and nephrology training at the Royal Children's Hospital, as well as Birmingham Children's Hospital and Nottingham Queen's Medical Centre in the UK. He's currently completing a PhD with Professor Melissa Little's Kidney Development, Disease and Regeneration, and Melissa Little received an award at the Congress, and she's done amazing things. You might have heard her name mentioned to do with the Eureka Prizes in 2015 for a kidney in a dish. And her lab does disease and regeneration at the Murdoch Children's Research Institute, which is part of University of Melbourne. His laboratory research examines the disease modelling capabilities and limitations of kidney organoids grown from stem cells of patients with genetic kidney disease with a specific interest in tubular disorders. He's the recipient of an NH and MRC postgraduate award and an RACP JACO NH and MRC award for excellence. Dr. Forbes will be speaking about ARPKD, which is the lesser known, slightly less frequent form of PKD, and we haven't often had speakers about it, so this is going to be really informative to all of us. So please welcome Dr. Tom Forbes.
Thanks very much. It's a real pleasure to be invited and to represent ARPKD. So I'm going to talk today about the genetics of ARPKD. I'm going to talk about the clinical features, spend most of the talk talking about the clinical features and the management that we currently have today. And I would love to have presented a long talk about all the numerous clinical trials and data that we have for treatments for ARPKD, but unfortunately we don't have that body of work. So I'm going to be speaking a little more aspirationally about how we're improving the care for children with ARPKD. Before I go any further, and because I know this is being recorded and going to be uploaded online, I'll sort of stop short of asking for a voluntary show of hands as to who's here, because they have a link to ARPKD. But this is a condition that is associated with a reasonable degree of morbidity and mortality for young babies. And so I think just if anybody's watching this online and maybe this is the first time they've really thought about ARPKD because they've got a pregnancy that may be affected, then you're more than welcome to contact me. I'll just go back. You're more than welcome to contact me using my Twitter handle @KidneyTom. You can direct message me, or you can get in touch with PKD Foundation Australia, and they can put you in touch with me, or together we can find someone for you to give you the information that you might need for your journey. So genetics. So this is quite a rare disease. It affects 1 in 10 to 40,000 children, depending on where you are in the world and which report you're reading. And it's predominantly due to one gene, which is the PKHD1 gene. And PKHD stands for polycystic kidney and hepatic disease. And hepatic is Latin for liver, really, so there's a liver disease associated with this as well. It's autosomal recessive, and I'll go on to discuss exactly what that means, but it's autosomal recessive in its inheritance pattern. And it has a large number of variants associated with the gene. So variants is the new term that we're using for mutation. We don't like the word mutation anymore. It's got a lot of stigma associated with it. So we call them variants now because we all have them. We all vary, and it's okay. It's just that some of these variants are associated with disease. So over 750 variants in PKHD1 in the registry, which is held in Germany. And the name of the protein that the gene codes for is fibrocystin, sometimes referred to as polyductin, often depending on which organ you're referring to, the liver or the kidney. So what is autosomal recessive inheritance, and how does it differ from autosomal dominant inheritance? We've already spoken a lot about ADPKD tonight. I think the audience here tonight is quite au fait with how a dominant gene is inherited. You only need one copy of the gene to develop some form of the disease, and that's passed on to 50% of your offspring if you've only got one copy. For autosomal recessive disease, you need to inherit 2 abnormal copies of the gene in order to develop the disease, because if you have one normal gene, that's enough to protect you from developing the disease. So the majority of cases that are diagnosed are born to 2 unaffected parents who are usually unknowingly carriers of an ARPKD variant. And 25% there's a 25% chance with each pregnancy that they will pass on those two affected genes to their child and hence make them affected by the disease. There's a 50% chance of their children inheriting only one copy of an abnormal gene and a normal copy from their other parent, and that will make them an unaffected carrier. And then there's a lucky 25% of children who will inherit both normal copies of the gene and have nothing to do with PKHD1 for their lives. About 1 in 70 people in the general population carry variants in this gene. So to put that into perspective, yes, it sounds like a lot, but to put it into perspective, this week we've got the Anzac Day game coming up at the MCG. We're expecting a full MCG of supporters, and it's probably 95 to 100,000 people there. And we would expect about 1,400 people in that stadium to be carriers for PKHD1, and most of them won't know it. And the chances of two people with PKHD1 meeting each other and having a child, and then that child inheriting both those abnormal copies, is about 1 in 10,000 to 20,000. I should say also that the other major difference between ADPKD and ARPKD is that this diagnosis comes as, not to trivialise the diagnosis of ADPKD in any way, but this diagnosis comes as a real shock to families because there's no history in the family. This is not something that's occurred. Everybody north of the affected child in the family tree has never had a PKD before. It certainly shouldn't if this diagnosis is being considered. So this comes as a real shock because it's usually diagnosed in pregnancy as well. And then the gene product is called fibrocystin. This is the protein, and we've heard from Sharon about the primary cilia tonight. And the primary cilia, as she mentioned, is a little antenna that sticks out of the top of every cell in the body, mostly. And it's there to detect flow, it's there to detect chemicals that are around the cells. And it helps the cell tell what's the front of the cell from the back of the cell, it helps the cell divide. It's got a lot of cellular functions that we don't know about as well. And the PKHD1 protein, or the fibrocystin protein, actually associates with the two polycystins that we've been discussing so far for most of the night. There's a little bit of conjecture in the literature about that, but most of the literature supports that fibrocystin engages in some way with PKD2, with the PKD2 gene product, polycystin 2. Beyond that, we don't really know much about exactly what this protein does, so we share that in common with ADPKD. And the other major difference is the way that the cysts develop. So, as I've already discussed, in ADPKD, you can get a cyst arise from anywhere in the nephron, and those cysts grow and bud off from the tubule and then expand and compress normal functioning tissue in the kidneys. In ARPKD, it's a bit different. We don't get any budding off, and we seem to get this dilatation of tubules in a very specific segment of the nephron, very late in the nephron, in the collecting ducts. And so the collecting ducts all dilate together, usually, rather than just one at a time, little cysts developing in ADPKD. And they cause a deterioration in kidney function in the same way that cysts do in ADPKD by compressing normal functioning kidney tissue. So that's all I wanted to say about the background and the physiology of it. We'll talk about the clinical features. And there's a wide variety of severity of this disease, which we usually define by when it is that a patient encounters dialysis or transplantation for the first time. So we can have babies that are born with very poor kidney function. We can have babies that are born despite an antenatal diagnosis with quite good kidney function. And then we can have some patients that are born healthy and with no antenatal diagnosis at all, presumed healthy until they develop another symptom and they get diagnosed later in childhood, and that can be a urine infection or a blood test that shows abnormal kidney function, or an incidental finding of high blood pressure which then winds up turning into a diagnosis of polycystic kidney disease. I want to focus to begin with on the antenatal diagnosis. So the majority of cases of ARPKD are diagnosed antenatally, and the findings that we often see are those found on a mid-trimester or late trimester scan, and they include large kidneys, bright kidneys, which are sometimes called echogenic kidneys, and that sometimes with the appearance of visible cysts. We can have abnormalities in the amount of amniotic fluid around the baby, and that's because the kidneys are slowing their production of urine, and it's fetal urine that contributes to the volumes of amniotic fluid around the baby. So if the amount of fluid is dropping, one of the reasons that can be is due to a reduction in fecal urine production. That can be normal, it can be reduced, or it can be completely absent. And that is a marker of the severity of the disease antenatally. That can go on to affect lung development. And lung development in ARPKD can be perturbed for a couple of reasons. The first being that reduction of fluid, because babies actually breathe their amniotic fluid in and out while they're being developed. And that helps expand the lungs, and it also delivers growth factors to the lungs to help the lungs develop in the right way. The other reason that the lungs sometimes don't develop very well is because there's a huge amount of pressure coming up from underneath. And if I try and use this mouse to show you on this ultrasound image here, this is a baby in cross-section, in utero, and you can see this is the abdominal circumference here that I'm drawing a circle around. This is the right kidney, so it's really occupying the whole part of the right abdomen, and this is the left kidney between those calipers there. So it's really quite enormous. You can see it again on this section, on this MRI of a baby, again in utero, very large kidneys pushing up the liver. And you can see there's a couple of abnormalities in the liver there as well, and a reduced space for the chest and for the lungs to develop. So whenever these diagnoses are made antenatally, of course, as for any antenatally detected congenital anomaly, these babies are referred for counselling, and they're usually seen by a neonatologist, a baby specialist, a paediatric nephrologist. I think it's absolutely imperative that they see someone with a good, sound knowledge of the full natural history of this condition, and sometimes a geneticist as well, as they embark upon genetic testing and counselling. We often ask for these babies to be born in a tertiary obstetric centre so that there's a neonatal intensive care support nearby, because these babies often need help with their breathing. It's not uncommon for them to require intubation, ventilation, and if for a period of days it's seeming that trying to help the baby breathe is very difficult, and it's thought that that's due to that mass effect of those very large kidneys in the abdomen, on occasion we will remove those kidneys, especially if they're not functioning very well anyway, because all they're doing is threatening that baby's ability to breathe. So we might remove one or both of those kidneys in an effort to help the baby's respiratory status. And with that, of course, once you've removed a baby's kidneys, and perhaps if their kidney function was sufficiently poor anyway, you need to commence some form of dialysis. And dialysis in babies can be very complex, but it's something that we're actually getting much better at, certainly over the last 10 years, I would have said. In babies, we're really restricted at the moment to peritoneal dialysis. It's incredibly difficult and high risk to perform hemodialysis in babies, but it is done. And the reason for that is that all of the machines we have for hemodialysis are made for adults. And the volume of blood you need to fill the circuit for hemodialysis before it returns to the baby is largely more than the volume of blood that's floating around in the baby to begin with. So that's why that's very difficult. Also, it's only recently that we've started to optimise our equipment for babies for peritoneal dialysis. So there was a time when we were using adult equipment or at least paediatric equipment to dialyse babies, paediatric Tenkoff catheters, paediatric sets, but all of that's slowly coming up to speed, or is up to speed, and we now have specialist neonatal sets and catheters that we can use to deliver peritoneal dialysis to these babies. For the babies who survive the early weeks of life, the outlooks are quite good, but they do spend an awful lot of time in hospital. Usually at least 3 to 6 months of the first 3 to 6 months of their life is spent in hospital after they've come off the ventilator. We need to optimise their medical status and their peritoneal dialysis. They often have difficulty with feeding. That's probably because we're using their tummies for dialysis, and so it's quite uncomfortable for them to take feeds. They often vomit. We need to educate parents how to do dialysis. And this is, as you can imagine, having a baby in hospital for 3 to 6 months is a tremendous psychosocial stress. It has implications for employment, it has implications for healthy siblings, it has implications for finances, among other things, and of course just general stress of having a very unwell baby in hospital. So we have a full social work and psychosocial support package that accompanies our medical care that we deliver I would have said, in any paediatric centre that looks after these babies. And dialysis is, of course, a bridge to renal transplantation for everyone. So, but for babies, of course, we need them to be big enough to accept the organ an organ transplant into their, sometimes into their abdomen, but usually in the same place that adults have their transplants put into the right iliac fossa. And that's around about 2 years of age, roughly, around about a size of 10 kilograms. So these babies are going to require at least 2 years of dialysis before they're eligible for transplantation, accepting that they have normal growth. But they're not hard and fast numbers. We do consider them on a case-by-case basis. And then the outcomes for these babies, unfortunately there's a death rate of around about 20 to 40% in the early weeks, and that's largely because of an unsurvivable lung problem, not a kidney problem. But of those survivors, the outcomes are very good. So 85 to 90% will survive to their first birthday, and just shy of that surviving to their 10th birthday. We do see some developmental delay, and that's probably starts early because we have these babies on their back getting dialysis continuously often and in the first few weeks of life, so they miss out on that opportunity to actually just develop, and they catch up eventually. And we're having, as I've mentioned, we have continuing improvements in our standard of care and the equipment we're using and the experience we've had. So the numbers that I'm quoting here are probably representative of an era prior to those developments. And if we were to survey survival rates in the modern era, they'd likely be higher. And of course, there are wonderful stories to come out of ARPKD as well. And this is our current poster girl for ARPKD at the Royal Children's Hospital. Her name's Aubrey. And she was one of those babies just a few years ago, during my fellowship year actually, who was born with severely abnormal kidneys. She had them both removed in the first week of life. She was on a jet ventilator for many weeks, and she started dialysis from that first week of life. And here she is, having received a deceased donor kidney transplant last year, loving life, and she's very cute. So that's what I wanted to say about the babies. But of course, there are plenty of babies that are born with an antenatal diagnosis of ARPKD who are born, and we're all prepared to jump in, and things just seem to be okay, and they're well, and they go home, and things progress well. And there are also children who are diagnosed later in life, and young adults who are diagnosed later in life as well. So what sort of clinical features do they encounter? As for ARPKD, high blood pressure is one of the real struggles that we have in these children, and they can have quite severe hypertension, sometimes requiring 3 or 4 medications to try and keep it under control. And similarly to ARPKD, we believe that this is primarily driven by compression of that normal functioning kidney tissue, and as it starts to fall under stress, it releases hormones that drive the blood pressure up. They can suffer recurrent urine infections, abdominal distension just by sheer size of their kidneys and liver. They often wee quite a lot because this problem is confined to their collecting ducts, which is where most of our water gets reclaimed. It's how most of us sort of conserve water. They lose that function, and so they tend to just wee and wee and wee. I often refer to it a bit like being a tap that can't be turned off, and they often just learn to drink to keep up with that. But we need to keep that in mind if they get gastro or some reason they can't regulate their own hydration. We need to step in and help them out. We do see reduced growth, although we're getting much better at managing that, and I think that's because we're much better with proactive nutritional management of these babies early on. They do vomit almost reliably and often, and we now quite proactively use things like enterostomy tubes, so feeding through the stomach, as a temporary and early measure. And we have a real focus on nutritional assessment from an early point as well. So we make sure that these babies are nutritionally sound, and then sometimes if their kidney function warrants it, we can add in some growth hormone. So that's not so much of an issue for the current era. We see electrolyte abnormalities, and we see liver disease. And the liver disease is quite a specific one. It's called a ductal plate malformation, or the eponymous name for it is Caroli's disease. And what you can see on this cartoon here, on the left-hand side is normal. That's normal bile ducts. So PKHD1 is quite critical. The PKHD1 gene, or the polyductin protein, quite critical for the development of bile ducts, just like your collecting ducts in your kidney. And what a normal bile duct looks like is a simple tube, a tube that can drain bile in one direction. But what we get in ARPKD is this ductal plate malformation, where instead of getting a tube, we sort of get this sheet that wraps around the veins of the liver. And I often use the analogy here of when you go camping, you're often told not to drink from stagnant water because it can harbour infection. You can grow bugs in it. If you go camping, if you're going to drink natural water, you drink it from a running stream. through these normal bile ducts you get nice unidirectional flow of bile. It can get through quite easily and that reduces your risk of infection. But in these big convoluted structures, you can get stasis of bile and infection within the bile, and that can lead to quite serious infections. This is a congenital abnormality. It does lead to fibrosis within the liver as well, so we can get a reduction in liver function. About 10% of children will require a liver transplant as well as a kidney transplant for this condition. And sometimes we do that at the same time because there is good evidence to suggest that for reasons we don't fully understand, having a liver transplant at the same time as a kidney transplant gives you some form of immunological protection of that transplant against rejection. We don't know why that is, but we see much lower rates of rejection in people that receive a kidney and liver from the same donor. And then, of course, there's progression of kidney disease. And it progresses indefinitely to a point where a child will need dialysis or a kidney transplant at around about 15% of this cohort every 5 years. And, of course, again, this is old data, 2005, so it's likely that advancements in care will have improved these numbers for the current cohort. I always say that, give everybody some hope. But what we can see here is that at the 25-year mark, we've still got 30-odd% of patients that have not yet reached the point where they need dialysis or transplant. So there's a huge variability in the severity of disease. And why is that? Well, it's probably got to do with genetics. So amongst those 750 variants that I described at the start of the talk, there are going to be some really severe ones, some that totally stop that protein from functioning at all. And then there are going to be some that might disturb the function of the protein a little bit, but not terribly. So if you end up having one very severe infection and one not so severe infection, you're likely to be on the more severe end of the spectrum with an antenatal diagnosis. If you have two, and the medical term we use is hypomorphic, which means it's a variant that will reduce the effect of the protein, but not severely. And if you have two hypomorphic variations in your genes, then you're more likely to have a later onset phenotype. And we don't understand this completely, and because this is such a rare disease, it's hard to really collect enough variants in one place to really be able to study it and make declarations about what's a good allele and what's not a good allele. So these are the international registries that are run out of Europe that most patients are now being recruited to so that we can try and answer those sorts of questions. Out of interest, if you are unlucky enough to develop two very severe or truncating variants in this gene, more than likely that pregnancy won't survive, and probably would be an early miscarriage, I imagine. And I just wanted to mention our National Renal Genetics Service, which has been one that's been built up over the last 3 years. It's called KidGen. It started in Queensland and it quickly spread down the east coast of Australia, and now it's everywhere. And KidGen is a consortium of nephrologists and researchers. More than one of us are in the room. And what we strive to do is to provide quality care to patients who have genetic kidney diseases. There are specialised clinics set up in every capital city that will take referrals for patients with suspected genetic renal disease, counsel the patients, arrange and pay for specialist genetic testing, and provide the post-testing counselling and follow-up as well as cascade testing throughout the family if a gene is found. They're also intricately linked with a set of scientists who are interested in furthering the understanding of genetic renal diseases. And these are not just for ARPKD, they're for all comers with inherited genetic disease. So that's the way that we manage these babies at the moment and young children. But what about future developments? So we had Nadia Rosenthal out at MCRI recently who gave a really lovely lecture about how science tries to inform medicine and some of the strategies that she's using for that. So Nadia was one of the founding directors of the Australian Regenerative Medicine Institute here in Monash, and she's currently working at the Jackson Laboratory in Maine in California. And I really liked her talk because she spoke about these three principles. It's predict, treat and prevent. Three things that we try to do as a scientific community to further medical disease. Try and predict who's going to be affected by a disease, try and improve the treatments that we currently have for them, and then try and prevent their disease from progressing by targeted therapy. So I'm going to provide one example of each of those. And this is the first one, to predict. So I'm not involved directly with this study, but I thought it was a good example. Mackenzie's mission is a pilot study that's examining the role of genetic sequencing, or genomic sequencing I should say, for couples that are planning on having a baby. So if you're planning on having a baby, you can be referred to this study, have a full genome tested, they'll analyse the genome and report back to you any risks that you have for having a baby with an autosomal recessive or an X-linked recessive condition. And they're examining the medical outcomes here, they're also examining the health economic impacts, because what they want to do is try and roll this out as a population-wide service, anticipating that the cost of that sort of sequencing will be low enough to facilitate that when the time comes. And ARPKD exists on this list, and if I'm not wrong, I think the PKD Foundation had a key role in making sure that ARPKD was on the list of, very appropriately I should think, of the list of disorders that were screened for. And this whole project actually came from this couple here. I think it's Jonathan and Rachel Casella, and their little baby Mackenzie, who was born with spinal muscular atrophy, which is a very severe neurological condition, and she died at just over 7 months of age. And they approached their geneticist and said, "We don't feel like it's fair that other couples should go through this. What can we do about it?" And he said, "Well, let's try this." And so they've actually championed this whole thing right from the get-go. So that's something that's on the horizon. Well, it's about to start in those 3 states. And if you're interested, then australiangenomics.org.au has all the information. So what about improving the treatments we already have? Well, I mentioned how we can't use hemodialysis machines for dialysis in babies. It's all about to change because, of course, some intelligent people in America and in Italy have developed a paediatric emergency dialysis system. And basically it just uses much smaller circuits, a different style of pump, and it's going to provide us with a really rapid ability to control fluid overload in these babies when they're admitted to neonatal intensive cares. And we know that fluid overload is a key factor that's involved in the risk of death for these babies. So if we can control fluid overload, we can certainly improve survival rates. And you can see in the graph down the bottom here, the red line on the top is illustrative of the fluid overload and how quickly they were able to get control of that. It also allows us to give the baby more medication, feeds, things that are important for their health, which are often restricted when we're trying desperately with peritoneal dialysis to get the fluid off. So this is Carpe Diem. We are looking at purchasing at least one of these, which will be useful not only for patients with ARPKD, but I think it will be really key in children that have cardiac operations at Royal Children's Hospital as well. And then in terms of preventing the development of cysts in ARPKD, well, unfortunately we don't have any current trials underway in humans. There are some mouse models, but they don't tend to replicate the disease that we see in humans particularly well, especially in terms of the development of renal disease. They get a good going liver disease, but we don't see the renal disease quite as prominently. So that raises a question as to how well we can extrapolate our findings from those mouse models into the patients we treat. All of the culprit molecular pathways that Professor Ong had highlighted are implicated also in ARPKD, which is one of the reasons why we think it works in context with the polycystins on the primary cilium. And there is the potential, of course, for stem cell therapies, as Sharon was discussing, and as I will continue to discuss, to try and bridge that gap between the bench and the bedside for these patients. That's all I had on ARPKD. Thank you.